Alright, let's get into one of my favorite units, y'all. Conservation energy. This is going to take definitions from all the work energy stuff that we have done so far and make our life a lot simpler. We're going to be able to solve for the velocity of things, or the speed of things, or the displacement of things very easily compared to Newton's second law and making our kinematic equations. We still might have to use some kinematic equations, but I think you'll like the conservation energy. It makes everything we've done easier. So first, let's talk about energy a little bit and systems and what kind of energy can be transferred. Well, we've seen that work can transfer energy from one thing to another. So if I lifted a book up, right, we're going against the force of gravity. I am transferring energy to the book, and it's now at some new position, some delta y above where I started, and now it has some mg delta y from that reference point, which I can turn back into something else. So work is one way to transfer energy. We'll see later in the semester mechanical waves transfer energy, literally vibrations and stuff. This could be sound. This could be the earth moving, right? Earthquakes even. Heat. That is, you're going to do a lot of studying or take courses on heat, thermodynamics. You're going to study the mechanisms and how energy transfer is driven because of maybe 2 points in space having a different temperature, some T1 and T2. That's going to cause a flow of heat. And heat is a very misused word, by the way. It is a method of transferring energy. It's not a form of storing energy. So it's for transfer only. But yeah, thermodynamics will teach you lots about that. We can have matter transfer. You'll see when we do conservation of linear momentum that we can actually have matter transfer of a rocket shooting out mass from the back end. But that's not what I'm talking about necessarily. I'm going to use the book examples on this one. And this is further in the book, or actually next semester maybe for you. But what happens if you filled up your gas and then took it to another location? Filled up the gas in your car, took it to another location. You just took energy with you to a new place, and it could be inside or outside our system now. Electrical transmission is another way. So we talked about power in the last lecture. Well, you've probably seen the word watt associated with electricity more than anything. But guess what? It's just a work per unit time, right? Just a refresher. Work per unit time is equal to what we call power. And basically what we can say is that if the total amount of energy changes in a system from one of these reasons it is because it crossed what we're going to call a boundary line. So we could have some crazy contraption where we have a pulley system or something. But we get to draw a box around this thing, and we call that our system. And as long as no energy leaves, so as long as no heat goes anywhere else, or sound or light, It don't lose any matter, anything like that. As long as none of it actually leaves the system, we can say that energy is conserved. And so we'll start off by saying that the total change in the energy of the system is equal to any of these mass transfers. We'll call it a capital T. T, not mass transfer, any of these types of energy transfers. T is energy transfer methods. All right, now I'm about to throw a bunch of terms down, but we're also not going to be using a lot of these terms in this class, so don't be overwhelmed. I'll show you my tricks and tips for this unit. I really like this unit, so just bear with me for a moment. What we can say if we expand this equation, if we had energy in a system, one, we could have kinetic energy, so let's throw down change in kinetic energy. We have change in potential energy. We could have what's called some change in internal energy. All right, so if we slide something across the ground due to friction, and we'll talk about that in just a little bit in more detail, the block is going to heat up. If you apply your brakes to your vehicle to slow down, you're turning friction into heat. Yes, you have robbed the system of mechanical energy. The kinetic energy is now less, right? We have a slower speed after it comes to a stop or slows down. But that energy cannot be recovered. It's a change in internal energy. This can actually be recovered sometimes. Just depends on the system. But in the case of the brakes, we can't recover it. But then let's list out all these different types of energy transfers. What do we have? Work. We can call mechanical wave transfer. We had the transfer due to matter. We had the transfer of energy due to electromagnetic radiation. We had the transfer from electrical transmission too. Well, we're not going to need to deal with this, or this in this class. And very rarely do we actually look at the change in internal energy in conservation of energy problems. So what we're going to do is first say that the total mechanical energy is equal to whatever the kinetic energy is for the system plus the potential energy. And I'm sorry if I change U with potential energy, it's also referred to as V. This is going to be in your future, or U. The potential is U. When you get into mechanics, specifically, they'll often call it V. Kinetic energy is interchangeable with T. So if I happen to write one of those, that's what they mean. I'll try to catch myself though. But I don't think I made a mistake yet. But if we say that the total mechanical or the total energy in the system is the kinetic energy plus its potential energy, and we're gonna consider like almost always isolated systems, meaning that no energy is going out. Everything is being stored back in. If we do lose some to friction or something, I'll show you how to subtract it from this wonderful equation I'm about to derive. But we'll say that if no energy leaves or goes outside our system, then the change in this E right here would be 0. If the change in the total energy of the system, So two things. One, the change in mechanical energy is going to be zero, this. But since it's an isolated system and nothing is going to be transferred outside the box, right? We got all this stuff going on here, all kinds of motion, but we draw a box around it and say that's our system. As long as nothing leaves or comes in, we will also say that the total energy of the system doesn't change, or delta E is equal to 0. And when we put those two things together, we get the conservation energy. We get the change in kinetic energy plus the change in potential energy is equal to 0. And you'll see this written in many ways. I like to think of this as an initial state of energy is equal to some final state of energy. Alright, what do I mean by that? It means that you'll see this definition broken up a lot of different ways. I like to automatically, if I can use the conservation energy, which in most of these problems in this whole unit, you can just jump straight to the conservation energy, even if there's work done, and I'll show you how. But right now we're not looking at work, we're just talking about the kinetic and potential energy. And the most common, or the easiest way to write this down is the initial kinetic energy plus the initial potential energy. Then you might see this as a 1 or a 2. So the kinetic energy at 1 plus the potential energy at 1 is equal to the kinetic energy final plus the potential energy final. So you could have multiple points. If it was a roller coaster, you could call this 1 and this 2. This could be your 3. So that's what I mean by these numbers right here. This could be the, if you're interested in what happens between, let's say, how fast is it going by the time it goes to 4 on this roller coaster thing, then we would look at the kinetic energy in its initial state at 1. The potential energy in its initial state at 1, and that's going to be equal to the kinetic energy at 4 plus the potential energy at 4. So just its initial final state, doesn't matter how we got there, right? All these, the only thing that matters is we saw that the path was dependent on was the conservative force of friction so far, or the non-conservative force of friction. If it's not just the frictional force times the direct path, right? It's if we took a frictional block up an incline, we have some friction going against us, our motion is up the incline. We would have a different amount of friction than if I went to the same level but took a path that was curved like this, that was actually longer, right? This one's going to have more work by friction. But here you go. This is huge right here. Conservation of energy. And I'm going to show you a couple tricks real quick. Because what happens if you have work? Well, work. What do I mean by work? What if there's a function of S? A force is a function of S, where, for example, I can't use conservation if I had some function of S like f of s is equal to 2s squared plus 3. There's no place to put it, right? Well, there is. We can take this kinetic energy initial plus potential energy initial, and then do plus or minus the work. And I don't know if you'll see this method in your text. It's always different in every text. This is just kind of how I was taught. And this will equal our kinetic energy final plus our potential energy final. So just put your work in here and put it in as plus or minus, because if this is our initial state here on the left side, initial, can't write, initial state. I still can't write. And this is our final state. If, let's say, we had friction, that would be minus the work done by friction on the left-hand side. We removed energy from the system. It is subtracted. If we had some function like this, we could put in the work done as the integral of f dotted into dr from some r1 to r2, or if it was maybe just a function of y, let's say this is 2y squared plus 3, then that becomes the integral of 2y squared plus 3 dy from y1 to y2. And this will come out as plus or minus. And you just put that there for the work. Friction, this case right here, or if they ever say x joules is lost to something, we could say friction. X joules is lost to friction. What is its final velocity? Well, let's just put a minus x joules in on that side. It removed it from our initial state, so let's put it on our initial state side, and let's put it in as a negative. So if x joules is lost to friction, let's say x is equal to 25, just to make it a little more clear, then we'd say the kinetic energy plus the potential energy is equal to, minus 25 joules is equal to the kinetic energy plus the potential energy. Oh, it's a mouthful. And then initial and final states. My last trick for this. You will learn that kinetic energy is always 1/2 mv squared. So I look at the problem and I say, okay, is there motion? Most of these, that's the whole point, right? We're in mechanics, basically. We're talking about everything that has motion. Doesn't have to, though. We can be in static equilibrium. But if anything has mass and has velocity, then it has a kinetic energy term, 1/2 mv squared. So just go ahead and put it down. Even if it doesn't have any velocity in its initial state, I still write it down. So that takes care of the kinetic energy. And then I look at the problem and say, okay, what kind of potential energies could we have? It could have some mgh1, and it could have some 1/2 kx squared. Now notice this is positive. It's always positive, and we just put it in on the left or right hand side for its initial or final state. If this is its initial spring stretch, I cannot spell that, x1. And then for our right hand side, then we'd put plus or minus the work. And then for the right hand side, I would say, okay, we have possibly some 1/2 mv final squared. If it's maybe trucking along at some different speed. Then there's also some mgh2, possibly, doesn't have to. And then we could also have some spring stretch in its final state, and so just put a 1/2 k x2 squared. These are both positive numbers. You don't have to think about which direction the work is being done by the spring. You just put in the potential and put in how much it's stretched in its initial, and then how much it's stretched in its final state. If it's something gravitational, if you're off looking at something at the ground, I find it convenient to put the ground at y is equal to 0. Or at least one of the final, or the initial or final point of the problem. So let's say it started on the ground and ended up here in space, maybe some projectile problem. We went through some delta y, so that's some potential energy mgh1 down here, but h1 is equal to 0, so we get to cross out that term. Boom. So I write the whole thing and then I cross them out. This is some mgh2 up here. It's potential energy due to gravity, and that would actually have a term, so I'd keep it. This problem doesn't have any springs. I'll do some with springs, I'll do some with friction, but I really recommend just writing out every type of potential energy that could be in the problem. Go ahead and write kinetic energy. If it's not there, cross it out, right? If it goes to 0, cross it out. Just don't forget it. The spring is always positive, so just put however much it's stretched. And real quick, something very oftenly confused, and I'll probably do a link to this problem from my 242 class. Let's say we had some collar. Draw actual rectangle. We got this collar that can slide down this pole, and attached to this wall over here is a spring. And we want to know how fast it's going after it drops some y is equal to 1 meter. What is the velocity down here? There's no friction or anything. We could say it started from rest. It doesn't have to, so it could have some 1/2 mv squared term. It definitely has some mgh term when compared to what I would call y is equal to 0 right here. But what I want to get to with this problem is, it doesn't matter that as this moves, the spring is working in a different direction. We don't have to f cosine theta it when we calculate the work or anything. All that matters is that it is stretched this much. Let me get a different color. It's stretched this much from its equilibrium position in its initial state at 1, and it's stretched this much x2 in its final state at 2. So the direction doesn't matter, but in this case we would have to know something about this distance. We do know something about this, and we could figure out what this is, or maybe we know the angle. We got to do some geometry to figure out what that stretch is in its final state. And then we always want to only consider the stretch or the compression. So make sure, don't forget that when you do a 1/2 kx1 squared, that this x is always from the equilibrium position of the spring. So in this problem, if it was not stretched in this initial state right here, you could say x is equal to 0, and it does not have a 1/2 kx squared term. We could just cross it out. Let's go ahead and sum up the energies in this problem. Let's do it. So what is the v at after falling some distance h? We'll do it like that. After falling distance h. And they give us this, let's say they give us a spring constant. It's unstretched in its initial state. So unstretched at 1. Well, I'm going to say the kinetic energy plus the potential energy in its initial states are equal to the potential energy plus the kinetic energy in its final states. Now, I said, let's just do my rule of thumb. I always write out every term. It was at rest, so it doesn't have a kinetic energy, but I'm still going to write it. It has some gravitational potential, and it has some spring potential. And we didn't have any work or energy lost in this system, so we don't have to worry about the plus or minus work. And let's say that that has some new 1/2 mv squared at its point down here at 2 after falling a distance of h. We could say it has some potential energy, but I'm going to call y is equal to 0 its final position, so we get to cross that out, make it go to 0. And it's going to have some more spring stretch. It could have had spring stretch to start with. We said it didn't, so we get to cross it out. We said it was relaxed in its initial state. It could, though, and we would just have to know that number. But it definitely has some stretch now if it didn't before, because it's in a different position, and by geometry and trigonometry we know that the hypotenuse is longer than either leg. So there is some stretch. Therefore, if I wanted to know the velocity, I could solve for that right there. Let's move this over here. I get 1/2 mv final squared is equal to mgh, and then this is a minus 1/2 kx2 squared. Start solving for this. I get mg, I'm just going to do it on here, divide by m, multiply by 2, and then we would square root it. So there's your final velocity for a problem that was initially at rest. Spring was at equilibrium, and we wanted to know the velocity after it fell some h. We could have had some spring stretch. It could have been stretched initially, like it could have been pulled tight right here, right? It would have just fallen slower, but notice we didn't find the acceleration. That's actually a much more difficult problem. If we deal with the conservation of energy, we just look at how much things are stretched, how much it fell through the gravitational field, how fast it's going, and there might be some work done, but in this case, any work done could be thought of as a energy term, and we were able to just use the conservation of energy. If you can do this, do it. And then remember, plus or minus work, I usually put on the left hand side, and you can do it on the other side too if that makes sense to you, but I look at it as being added or removed from the initial state of the system. Friction removes energy from the initial state, it would be minus. Alrighty.